And here we go. Thank you so much for joining us for another HRAI webinar. Today, we are presenting Mastering Control Systems for Optimal Heat Pump Performance. We've got Mary Mantai, General Manager with HVAC Designers of Canada. There she is on the screen right now. And Jérémie Léger, Project Leader with the LEEP team at CanmetENERGY-Ottawa. If you can't tell, he's the one with the headset right next to Mary. Before I let them do their thing, I'm just going to do a couple housekeeping items. First of all, thank you all for attending. Summer is a busy month for the HVAC community, and we appreciate you joining us for lunch to learn something new. If you'd like to ask a question, we're going to be holding those to the end of the presentation, and you can join the conversation by clicking on the Q&A button at the bottom of your screen, putting your question in there, and I will read it to them. Or you can hit us up in chat, and we can get those questions off as well. If you'd like to put on a webinar of yourself, please reach out to myself, mbradford@hrai.ca. We can arrange a webinar of another thought leadership topic. And if you just want to see past webinars, you can check out HRAI's YouTube page, where we've got all of them there for your viewing pleasure. But that's enough of me. I'm done rambling. Mary, Jérémie, off to you. Thanks so much.
Thanks, Matthew. So I'm just going to take a few minutes before I hand it back to Jérémie to introduce HVAC Designers of Canada, talk a little bit about who we are for those of you who are not familiar with us. So we're a national association representing heating, ventilation, and air conditioning designers across Canada, and we work with other stakeholders to deliver comfort and value to HVAC systems in Canada. So that includes HVAC legislators, building sector organizations such as HRAI, manufacturers, installers, contractors, builders, and other government agencies. Next slide, please, Jérémie. So our focus is four main things. That's advocacy, quality, capacity building, and industry standards, with the goal of creating comfortable and efficient indoor environments in residential and small commercial buildings. So we are supporting and promoting the growth of the HVAC design industry, doing that all across Canada with a variety of different projects right now. We want to maintain and enhance the quality of HVAC design in Canada, add some regulation to the field. We want to make HVAC services available to all Canadians. So there are certain areas in Canada where it is not as common to have HVAC design, and we're trying to change that. And then to clarify and improve the HVAC design standards in the industry. So if you'd like to learn more about us or become a member, you can scan this QR code to go to our website, or just visit us at hvacdc.ca.
Great. Thanks, Mary. Great intro for HVAC Designers of Canada, and having been involved with them for some times now, I'd say that they're really leading some great work to make change in the industry. So thanks for that, Mary. So today we're going to be talking about mastering control systems for optimal heat pump performance. So this is kind of a series taken from our flagship heat pump workshop series that we're delivering across the country. So we'll be walking through some of the best practices or some of the differences between different control options and what might be best for your systems. So first, I wanted to do a quick intro into what is LEEP. So Local Energy Efficiency Partnerships is the long form, or just LEEP. You might know us from having come to one of our forum or workshops in the past, but we do work with Canadian industry to make homes more resilient, energy efficient, and affordable in the face of climate change. So how we do that is we reduce industry time and risk in adopting new technologies and building innovation. So we're trying to get some innovative technologies such as heat pumps into the hands of builders, renovators, contractors such as yourselves to get higher performance housing across the Canadian market. So we've been in operation for 15 years. We've ran events in 10 provinces, in all 10 provinces, and 25 plus municipalities. We typically work with manufacturers bringing specific equipment to the table as we discuss these technologies. So we've worked with 50 plus manufacturers through the years, and currently through various agreements, we are running roughly 50 to 60 events per year. So there's different elements that goes into some of our workshops. So we cover different topics from integrated design process to, we've been looking into adaptation and resilience, electrical load management. We talk about operational carbon, embodied carbon. We looked at envelopes, windows, and fenestration. This piece that we're going to be looking here today is more specific on our heat pump initiatives and high performance mechanical initiatives. But we do have content on solar PV as well as numerous case studies and field trials that we've shared with industry. So if you're looking to engage in any of those topics, LEEP can be there to help you navigate some of the new technologies that are out there. So this is a slide taken from our partner organization, the Office of Energy Efficiency, where they ran a study and on what was motivating homeowners, or where were homeowners going for information on heat pumps. And by no surprise, I'm sure it's not going to surprise anyone on the call today, contractors are the key person or the key industry stakeholder that homeowners will look to for advice on heat pumps, when particularly in the retrofit space. They're not looking at Enercan's website or the utilities website for information. They're really looking at you as contractors to let them know what's the best system for their home. So part of the exercise or the initiative that we're taking on heat pumps is trying to get into your hands some of the business cases, some of the best practices around heat pumps, so that you're better equipped to advise homeowners. So quick agenda for today. So we're going to be looking at current market offerings and controls. So we're just going to take an overview of what these are, what controls approaches are out there. We're going to take a detailed review of these control approaches and look at them through the lens of a case study. This is a Toronto home case study that we're going to be looking at, and we're going to see how those control approaches are performing differently to each other, using the same heat pump system, just controlled differently for this particular case study. I'm also going to quickly touch on mini split controls, some highlights from previous sessions that we've done in the Maritimes, where split systems are fairly popular when going to from baseboard heating to mini split systems. And then we'll wrap it up with end goals and takeaways, and have plenty of time at the end for questions from the groups. I'm hoping to have a bit of a discussion towards the end, because I think that's always most valuable. So there's, if we look at central systems to start with, we could have electric or gas backup systems. They're a bit different in the way that we're able to control them. Electric systems are typically set up in a way that allows the supplementary heater to operate simultaneously or in conjunction with the heat pump. So that means that I can have my heat pump running. I can also have my supplementary heater running at the same time. This is a bit different from natural gas system, where that's not necessarily possible. Typically, they're configured in a way that we have to either operate the gas furnace or the heat pump. We can't really do both at the same time, but we could do one after the other if we have enough time delay to let things settle. So some of the control approaches that we're going to be looking at today are going to leverage that option and enable our heat pump to run below the thermal balance point of the home. So what are those control approaches that we're going to be looking at today? So we're first going to be looking at probably the most common one. It's an outside temperature balance point cutoff. We'll be looking at a single temperature point economic cutoff. So if you were to pick one cutoff temperature, what would be the one that minimizes your operational costs over the winter season? We're going to be looking at two stages approach, one that's temperature driven, one that's time-based driven. And then finally, an hourly economic cutoff temperature that a few thermostats have now implemented and are out in market that you can get your hands on. So why should we care about our selected control approach? Homeowners might have different goals that might be installation costs, operation costs, or primarily achieving comfort in your home. So if we can align our control approach to try to best meet some of these goals, so selecting the right equipment and then control approach that goes along with it, we'll get a happier customer. And that's going to help you as contractors not have callbacks, be more competitive in your business case as well. Obviously, from our end and from many utility and incentive programs, energy management and environmental impacts of running these systems is important. So we could pick a control options to benefit the environment as well. So we're going to be talking a lot about balance points today. So I thought it'd be worth just doing a bit of a review of what is the thermal balance point. So here on this graph, we see on the horizontal axis, the outdoor temperature that a house would see. And then on the vertical axis, the heating load or the heat pump capacity. So depending if you look at the blue line, we're talking about the heating load. If you look at the orange line, we're talking about the heat pump capacity. And the main point is that the heating load of the house is fairly linear. At around 15 degrees C, we generally don't require any heating. And as we get colder and colder, we approach that design temperature in Toronto, which is going to be our case study for today. I think it's around -18, looking at the graph. And we're going to have more and more load requirement. At the same time, we do know that heat pumps lose capacity at colder temperatures. So that orange line, you see that the heat pump is losing the ability to provide heat to the home. And as it gets colder, it has less and less of an ability to provide heat to that home. At some point, the heat pump's no longer going to be able to keep up with the load of the house, and we'll call that point the thermal balance point. So that's the red dot that you see, the intersection between the blue line and the orange line. So that's an important concept to memorize as we look at these control options, because we're often going to look at what happens above the thermal balance point and then what happens under that thermal balance point. If we want to be able to calculate that thermal balance point, we do have tools. So Enercan's air source heat pump size and selection tool is a great resource for that. It's an Excel-based tool. I've put a QR code here. If you can put in your heat pump data, the load of your home, and it will tell you what the thermal balance point is for that particular heat pump. So that's an interesting resource. Just kind of segue here for some of the tools that we have. It also allows you to do some energy and cost performance analysis, you'll see in the presentation today, and then understanding the loads and capacity curve for better sizing, and it's going to help you out in sizing systems. We are also coming out with a web app version of this tool, and that's coming soon. So let's look at the details of what these control approaches look like. So the first one that I wanted to discuss is the cutoff at the balance point temperature. So in this case, that Toronto home with a 3-ton heat pump system applied to it, that 3-ton system was limited by the ductwork of that home. So we couldn't go bigger because the ducts couldn't handle the extra capacity. We're going to look at a thermal balance point of -3. So what does that mean? It means that above -3, we're in the orange band here. So in this graph, you're seeing the outdoor temperature over the 1 year in Toronto. So in that orange band is when the heat pump would be taking over and providing space heating for the home. And then under that temperature, so in that red band that you see on the bottom, the gas furnace will 100% carry the load of the house. So we're doing kind of a straight cutoff. At -3, we're switching from heat pump to gas furnace. So that's a first control approach, and probably the most common way that heat pumps are set up today across the country is setting a balance point that sometimes calculated, but more often kind of a good guess at, or from experience of what folks think is an appropriate balance point. But that changes quite a bit from heat pump to heat pump. So it's actually better to calculate what that balance point is. Control approach 2, we can look at a single point economic temperature cutoff. So instead of looking at if the heat pump can keep up or not, we're now looking at, is it more cost beneficial to run the heat pump or be running on electricity or to be running on gas? So because the COP, or the coefficient of performance of the heat pump, does vary with temperature as well as capacity, there will be at some temperature, at some performance metric for the heat pump, it'll be better to run the heat pump or the gas furnace. In this case, for the model heat pump that we have, it just so happens, because gas is fairly cheap, that plus 3 degrees C was that kind of ideal sweet spot over the year, would minimize cost if we set that cutoff. That does mean that the heat pump, just like the previous control approach, would operate above that temperature. So if it's more than plus 3, then we're running the heat pump. If it's below plus 3, we'd be running the gas furnace. Now getting into maybe more interesting control approaches, in my point of view, is kind of staged approaches. So the first one that I wanted to cover is kind of a temperature-driven approach. So if we look at what it looks like at warmer temperatures, maybe we have a set point temperature, and then the temperature starts dropping in the house, and then eventually we reach kind of a first stage. Maybe it's set 0.5 degrees below that set point. So we want to maintain the house at 22 degrees. It falls to 21.5 degrees, and the heat pump kicks in. Because it's cold enough, the heat pump will heat the house, and we're all set. We've reached our 22 degrees once again. If it gets colder, it's going to react a bit differently. So again, at 21.5 degrees, so if we look at, we have our set point, the temperature starts dropping, and then stage 1, or that first stage, would activate at 21.5 degrees C, but it's not enough to get the house warmed up. So the temperature will keep dropping at a different slope, and eventually reach kind of a second stage where maybe a degree below set point will activate our gas furnace. So at this point, the gas furnace will kick in, the heat pump would have turned off, and the home will reach its set point. What this is allowing us to do is to get part of the heating load covered by the heat pump. And we're going to see later on that that can be quite significant in terms of how much heating we can cover with heat pump by doing this, because as soon as we reach below our balance point temperature, we're going to need some form of backup system. And if we can maximize the use of the heat pump, we're going to get better efficiency of our overall system. So a fourth control approach would be kind of a time-based approach. So similarly here, we're trying to activate the heat pump first and let it run for a certain amount of time. So instead of using temperature as the driver here, we'd use a timer. So we have a set point, the temperature drops off. Maybe we let the heat pump run for 15 minutes. If we don't reach our set point in 15 minutes, then we turn off the heat pump, we turn on the gas furnace, and we reach our set point eventually. Some controllers are going to be kind of a hybrid between 3 and 4. We've separated them here just so that we have a better view of how each are reacting if we just have that one approach. And the fifth approach is probably the newest one available in the market, is an hourly economic cutoff temperature. So similar to the other approach 1 and 2, where we have a cutoff temperature, now we're going to look at it on an hour-by-hour basis. So in Ontario, we have time of use, electricity rate. So the decision making around do we run on gas or electricity could change from hour to hour based on the cost of electricity. So here, depending if it's cheaper or if it's more expensive to run gas or the heat pump, we'll make a decision at each hour if we're running the heat pump or the gas furnace, and that's going to vary with temperature. So it's going to look something like on this graph. So the orange line here is kind of when we should activate the heat pump versus the gas furnace on a day. So we have kind of a 24-hour day that's displayed here. Those triangles are when we're running the heat pump because the efficiency of the heat pump or the cost effectiveness of running the heat pump is better. So here it's off-peak hours in Ontario, and then on peak hours and mid-peak for this particular day, we're running our backup because it's more beneficial in terms of cost. But that could change from day to day depending on the temperature of that day. So we've looked at 5 approaches, mostly in the context of retrofits. I just wanted to touch on what it would look like in new housing and just point out one specific clause in the National Building Code that looks at temperature control. So in 936.3.6, there's 2 elements that I think are not as known in the building code, which is touching controls. So the first one is looking at heat pumps equipped with supplementary heaters shall incorporate controls to prevent supplementary heaters to operate when the heating load can be met. So what does that mean? Essentially, if your heat pump can meet the load of the house, you should be running your heat pump according to 936. If it can't meet the load of the house, then you can go and use your supplementary heater. So knowing that thermal balance point becomes important because then you know when to operate your heat pump versus when to operate your backup system. Obviously, there's an exception here because on defrost cycle, you could run your supplementary heater so that you're not cooling your space during defrost cycles. The other point, again, touching on controls, is that heat pumps with a programmable thermostat shall be equipped with a setback control that will temporarily suppress electrical backup or adaptive anticipation of heat pump of the recovery point. So essentially here we're trying to, if we put a setback on our thermostat, we're trying to activate the heat pump first and not activate the backup system right away so that we don't end up in a situation where as we do backups, and it's fairly common, I think, in some controllers that if the temperature difference is too high, they'll go straight to backup and the heat pump won't really have a chance to provide sufficient heating. So you have all the best intentions of running a temperature setback at night and then the morning hits and your gas furnace kicks in pretty much every day because the heat pump's not let a chance to heat the home because it'll take a longer amount of time for the heat pump to do that. So it's just kind of a clause there to have the heat pump run first and in an effort to get more energy efficiency out of these systems. So there's plenty of thermostats out there. They're all kind of different in their control approach. So it's important to understand what control approach is being implemented by the thermostat you're installing. It might change what your recommendation on the thermostat might be, and all that in the context of what are the homeowner goals. So let's look at a case study and the impact of these various control approaches and see how we could adjust our control strategy or our selected control strategy so that we can better meet a homeowner's goals. So this is a Toronto case study home. It's a year built in 1922. It's 1,600 square feet. It had a gas furnace that was roughly 80,000 BTUs per hour, 96% AFUE. So they had changed their furnace at some point. in recent times. They had a heating load of just under 60,000 BTUs per hour. There's no cooling installed. The cooling load, I believe, was just above 2 tons. And we had a measured maximum airflow of the ductwork. So as I mentioned earlier, this house is limited by the ductwork in terms of how much of a heat pump we can put in. So the maximum heat pump we could put in was a 3-ton system. Otherwise, we would have gone over in what the ducts can handle. And it's going to be fairly common in natural gas markets for us to not be able to meet the full load with the heat pump. So we need some kind of backup system to really meet the full load of the home. So this is the case for this Toronto home. The homeowner goals were having resiliency to changing energy costs. They wanted to reduce the reliance on fossil fuel and manage costs, minimize disruption under renovation required. So they're picking this system. They're not going to rip out drywall and change ductwork to be able to put a bigger heat pump. They're going to live with a smaller heat pump that can't meet the full load and have a backup system. And I think that's going to be a fairly common case in natural gas markets. So what does it look like if we start comparing cost, energy, and greenhouse gas emissions for these different control approaches? So what we have here, now I'll take some time to explain the first graph in detail, and the other ones are kind of similar, just the horizontal axis that's changing. So in blue, we have the contribution of the heat pump in terms of the heating energy cost for the year. In orange, we have the heating energy costs associated with the gas furnace. And then on top, you'll see the total energy cost on the bar graphs. So on this graph, we're looking at energy cost. So on the horizontal axis, and we have for each bar different control approaches, the ones that I've just described. So the balance point temperature, the economic balance point temperature, a 2-stage temperature driven, 2-stage time driven approach, and an hourly economic temperature approach. So in this case, it's no surprise the hourly economic approach was winning out in terms of being the one that's the best cost performer. So utility cost for the year for this homeowner in Toronto would be just above $1,600. In contrast, the approach that utilizes the heat pump the most, so that 2-stage temperature driven one would cost around $1,980, so $1,986 per year to run. So there's about almost $360, $380 difference between those two. So that kind of the one that is the worst cost performer versus the one that's the best cost performer in this case. So we're looking at just over $300. If we look at energy performance, comparing these cases, it's a bit of a different story. Again, blue bars is the heat pump, orange bar is kind of energy supplied to the furnace. And we see that two clear winners. The staged approaches are really minimizing our energy consumption. And the best performer here is that 2-stage temperature-driven approach. So we're letting the heat pump run and activate at half a degree colder than set point, and then the gas furnace only kicks in if we go 1 degree below set point. If we contrast that to like the worst performer, we're about double the energy consumption on the single point economic temperature. So a bit of an interesting case there on energy. It's going to be reflected in terms of the greenhouse gas emissions. And I think this is for those homeowners that are environmentally motivated. This could be interesting. So we can save about just over 4 tons of greenhouse gas emissions of CO2, equivalent CO2, between the single point economic temperature and the 2-stage temperature-driven approach. So we're below a ton of CO2 a year for that best case scenario in this case. So if we wrap that all up in terms of a table and line that up with what would be homeowner goals, different approaches are going to be excelling in different areas. So if we talk about resiliency to changing energy costs, that hourly economic approach is really good. If the time of use rates change, if the gas prices rates change, we can always adjust those hourly economic factors, and we'll always get kind of the best solution that minimizes costs. So approach 5 is really good at doing that. If we are looking at reducing our reliance on fossil fuel, then staged approaches that are letting that heat pump run a lot more are really going to be an advantage here. So it's a bit of a different goal, different control strategy. And if we're looking at reducing operational costs, the ones that are minimizing costs obviously are the ones that are outperforming the ones that are getting more heat pump usage. What's happening here is that at colder temperatures, the heat pump COP tends to drop, so it becomes less economic to run the heat pump. So the more usage of the heat pump at those colder temperatures we do get, the more will increase costs, but we'll also be saving a lot more in terms of greenhouse gas emissions. So there's a bit of a trade-off there. So depending on what the homeowner goals are, you might select a different control approach is the main point. So I also wanted to do a quick note on all-electric mini-split systems in the context of baseboard heated homes, and I think there's some interesting notes there. So there's some challenges with ductless split systems. So ability to provide whole home heating and installation. So we're talking in the context of a retrofit. So often we'll put like the one head in the great room. We don't know how much coverage we're really getting in the bedrooms. Even if we put one head in one bedroom, it won't go to the other bedrooms. There are solutions there, like those ductless flat units that you could duct the bedrooms. But in general, those are less popular. So there are some challenges of getting good coverage with split systems. We're installation and design costs when using multiple indoor heads. So we might have multiple indoor and outdoor units, and that could lead to some design and installation costs. Meaning backup heating needs, especially in colder climates. So essentially, it's very often we're going to also keep our baseboards to have some form of backup, and that heat pump is going to have to work collaboratively with those baseboards. So we want to make sure it's an all-electric system. So essentially, what's going to reduce cost, operational cost, is also going to reduce energy consumption, and that's also going to reduce greenhouse gas emissions. So it's kind of the more we use the heat pump, the better it will be for the homeowner on all three fronts. So we should set up systems so that they're set that way. But we have to deal with the baseboards as well. And oftentimes we're dealing with two separate controllers here that are competing in the same space. Like I said, so we end up with kind of a dual control scenario in the same space. And to really optimize performance, a control strategy is really going to need to minimize the risk of baseboard overusage. So we don't want them to kick in if the heat pump can keep up. We're going to have some limitations with different types of baseboard controls. It could be like a really old thermostat has a wide band, and it's hard to really know when it's going to kick in for the baseboards. We want to avoid unintended consequences of increased cost, lower energy efficiency, heating and cooling at the same time, which is all things that have happened in the past. Homeowners forgot to lower the baseboards. Air conditioning season comes in, and you're cooling and heating at the same time. It's been seen before. And then limiting homeowner behavioral risk. So even if you set up the system one way sometimes. The homeowner might play around with settings. Are there ways that are more robust to prevent having the baseboard turn on too often? So it's like to propose there's like 3 major ways that controls could be set up here. The first one is kind of you set your baseboard to the same set point as your heat pump, and then you just see what happens. So you might get mixed results here. Maybe your heat pump kicks in before your baseboards. Maybe your baseboard kicks in before your heat pump. If your baseboards do kick in before your heat pump's rarely going to operate. So it's kind of a worst case scenario. You don't want that to happen if you're installing a system like that. When we're talking stage controls, so I think a lot of contractors, that's probably the approach that's most common. We're going to go and we're going to set the thermostat of the baseboards at a lower set point than what we're setting the heat pump to. That I think that could work great. So it allows the room temperature to drop before the heat pump will no longer have capacity to keep up, and then the baseboard will kick in. But there are some inherent risk with that. It might be your middle of January, a homeowner is feeling a bit cold because the approach requires the set point to dip a bit lower. Maybe turn on their baseboard heaters a bit higher, and all of a sudden they forget that they did that, and they're running the baseboard heat for the rest of the season. So you want to avoid those types of situations. So there are integrated controls that allow us to have one controller for the one space. So instead of having 2 thermostats trying to compete in the same space, we can integrate them together. And it's usually the heat pump controller that will take over and control when it allows the baseboards to turn on or off. So I just wanted to flag that's an option out there. If you're doing larger buildings at Part 9 that we're mostly discussing today, so for in like Part 3 MERBs, that would actually be a requirement of the National Energy Building Code to interlock baseboards and the split systems. So don't leave it to chance. Make your integrated controls decide when those baseboards are running so that you can really maximize the use of the heat pump. So final thoughts on, there's other things that are contributing to comfort that you might want to consider in terms of controls, especially if we're looking at centrally ducted systems. Continuous air circulation, helping to destratify the spaces can be helpful. Having thermostats that enable the variable capacity of equipment and enabling it to run on low. If we're talking about dehumidification in summer, having systems that can operate at low capacity and slow and get really a lot of water out, it can be important. So another considerations when we're looking at controls, setting up the thermostat, it seems simple, but it's often very, very much overlooked. Just actually setting it up so that it's running properly for that particular home. That thermal balance point is not going to be the same from one house to another, from one system to another. So that means that at a minimum, there are some settings to be changed at the setup stage of these systems. And then finally, homeowner education, letting them know how to operate these systems is very important. So what have we learned? So there's different current market offerings in terms of controls. So those different options, depending on what the homeowner is looking for, you might choose a different option if you're trying to minimize costs, if you're trying to be good for the environment. So choosing the right one for those goals and given the location and equipment that you're selecting is important. So there's a bit of an analysis there to be done. Detailed review of various control approaches. So we've gone through those control approaches. So the balance point cutoff temperature, which is not really optimized for cost or for energy efficiency or environmental benefits. So maybe one that's less interesting. And then single temperature cutoff points. So if you're trying to minimize costs, that could be one way of setting that cutoff temperature at that optimal point. And there's different staged approaches, and those are generally better in terms of environmental performance. And then the hourly economic cutoff is generally better at minimizing costs, but in markets where gas is cheaper, it will favor running that gas furnace a bit more than the staged approaches. And finally, just integrated split systems with baseboards. So trying to have control systems that, see the whole picture and not having competing system in the same space is definitely better practice. Finally, we looked at a case study and the impacts of different control strategies on this Toronto home. And we could see that it's vastly different from one control approach to another if we're looking at optimizing cost or greenhouse gas emissions. So it's not as simple as the one solutions fits all. It's really a discussion with the homeowner and coming back to what options are available in the market. And with that, it leaves us just over 15 minutes for questions. So I'm hoping to have a bit of a conversation with all of you.
Excellent. So I got a couple lined up, but if anyone wants to ask a question, at the bottom of your Zoom screen, you'll see the Q&A button. Pop it in there and I can read it to Jeremy. So let's start with Alex's question. Anyone compute the energy savings variance, all the other things being equal, between outdoor temperature cutoff control versus temperature drop strategy?
Sorry, could you repeat the question? I missed the first bit there. Yeah.
No worries. And if you droop strategy, my apologies. Has anyone computed the energy savings variance, all the other things being equal, between outdoor temperature cutoff control versus temperature droop strategy?
Yeah, so if you're just doing a straight up cutoff temperature at balance point versus a droop strategy, and have we computed the energy consumption difference, all else being equal? Do I understand that right?
I believe so, yeah.
Yeah. So yeah, definitely so I think if we go back, so a droop strategy would be effectively what we're calling our two-stage temperature-driven approach. So if we look at energy performance, and this is fairly common from market to market when we've done this. The balance point temperature usually falls between the staged approaches and the economic ones. Because generally gas is cheaper, so you cut off the heat pump earlier in the economic approaches than you would on a thermal balance point approach, but you get less heat pump usage in the thermal balance point approach than you would in the stage approach. So you generally end up with kind of not optimized for cost, not optimized for energy on a thermal balance point approach. It's kind of sitting in the middle in most markets that we've seen.
Thank you very much. Hope that answers your question, Alex. One from Patrick, I guess this is for me, asking if a recording of this webinar will be made available. Absolutely. You can find it on HRAI's YouTube page after the fact, usually within about a day. From another attendee, suggestions for a dual fuel thermostat brand that can accommodate Approach 5.
There's a few out there. Napoleon has a product. BKR, just kind of cloud-based, is integrated in a few products as well. They have their own thermostat, I believe. Those are the ones that I've seen. There might be others. I don't want to say that the others don't have it, but those are the ones that I've seen.
One from Brad, a comment, maybe you can comment on his comment. I have not found a control that will switch from heat pump to gas heating automatically to optimize time of use electricity costs.
Yeah, so those two that I've just mentioned, they would be able to do that. I think they're set up on, they're all automatically pulling gas prices and electricity prices based on your location, and they're all cloud-based, and they're kind of making that calculation on an hourly basis.
Thank you. Again, those are the questions we have so far. If you'd like to ask any in the, I guess, the 10 remaining minutes we have. In the meantime, do you have contact information you can put up or in our chat for people to reach out to?
Absolutely.
Yeah.
I'll share it with you
Mhm.
afterwards, and then we can
Yeah.
we'll send it out when we send the presentation, I guess. Yeah.
Sounds like a plan. Patrick has a question. Was cost analysis completed using Ontario's ultra low overnight rate structure?
So we haven't done that. It would reduce costs significantly for some scenarios, but in general, so we haven't done the analysis. We've only done the more standard three different rates. So on peak, off peak, and mid peak type rate structure in our analysis, just because that's the most common one that's employed. Yeah, but it's definitely doable. Yeah.
Excellent. Another question for me. This is great. I've never had so many questions. My email address, if you'd like to set up your own webinar or you've got questions about this, is mbradford@hrai.ca. I'll put that in chat, but let's get back to the questions for Jeremy here. I'm going to read another comment. Maybe you can comment on the comment. Using option 3 uses very little gas. In that case, is it worth paying the service charge for gas? That is, if you replace the gas backup with electric and switch to the DHW to electric or heat pump and save the $23 per month service charge, what is the net cost? This sounds like a high school exam question to me, but yeah.
Yeah, I haven't done the analysis on this particular home. The right now, if we it's what, like at most a $300 premium going to approach 3 per year. So if you switch to an all electric home, to my knowledge, it typically gets you in a better spot with utility rates. You're right. But we were going in the context that they were keeping their gas service charges. So that wasn't included in our analysis, but it certainly does play a factor in that analysis when we're
Kind of a
selecting
follow-up.
systems. Yeah.
Yeah, kind of a follow-up to that question. Does the cost analysis include carbon pricing for gas?
It does, yeah. So the cost analysis includes all service charges that are per kilowatt hour or per meter cube. So essentially, it includes like any transport charges that are variable by how much usage you get. And it's usually split in between kind of a fixed charge and a per usage charge. So that's all included, including taxes in the analysis.
Thanks so much. Now the questions are rolling in. Do you have an example of a central heat pump cost analysis for a customer utilizing propane as the primary heating fuel?
We do. There was a study completed by my colleagues, Alice Ferguson and Jérémie Léger, a couple of years back. They looked at propane, oil, natural gas, and all electric homes across the country. And generally, what was found in that analysis is that if you're heating with oil or propane, there's a good business case for you to switch to a heat pump. As well as if you're on all electric. So it just only on the natural gas cases where it was a bit more depending on the price of natural gas, and if you cut off the natural gas line, then those are like specific scenarios that would kind of tip the scale whether it was economic or not. But generally, you're increasing costs if you weren't disconnecting. But that might have changed. Like, it was a study done in 2018, 2019. So we like that's price of gas has changed and it'll keep changing. And price of electricity changed and it'll keep changing. So that analysis almost has to be repeated from year to year to really have a good sense of what's happening this year. But the general trend, if the carbon tax keeps going up, we would expect that the more emitting fuels would increase in costs, which would eventually favor heat pumps. So if you're looking kind of long term over a 15-year period, that heat pump, running that heat pump much longer might become more attractive. But that's just that's speculative, right? On what gas prices might be and electricity prices might be.
So, let's go for an anonymous question here. In your case studies, are you meeting the requirement that the heat pump must run whenever it can meet the heating load?
So no. So this is because it's not because we're in a retrofit scenario, we kind of analyze those different cases. So the cases where we're not meeting that requirement in the building code would be approach 2, where we're cutting off the heat pump before. So if I recall, it's +3 degrees C that we're cutting off the heat pump and then running gas, versus approach 1, which is the thermal balance point, which would be like what code is telling us, run the heat pump below that thermal balance point, and then after that you can do whatever. In this case, we're running gas. And then approach 5, depending on the cost of electricity. So I'm not remembering what the off-peak rate versus gas ratio led to in terms of we can maybe go see. So it was, yeah, roughly the thermal balance point is where it was. So in this case, it's meeting it off-peak, but it's not meeting it when we're on peak or mid-peak. It wouldn't be meeting that requirement. So the economic approaches are the ones that were a bit different. It would definitely, so the stage approaches and the 2-stage time approach are definitely meeting that requirement, because if the heat pump can meet the load, it's running and covering the full load in this analysis.
Question from David. What's the next step? That is, what technology, incentives, or programs are coming in the future to help installers and contractors? This could be a whole webinar by itself. But,
yeah, so I can't comment on incentives.
Yeah.
But from our perspective in LEEP, we're definitely trying to get the message out there in terms of proper controls and how to set up controls. So we'll definitely be enhancing our materials on controls to better support contractors. Connecting you with manufacturers of these controllers, so that you're aware of the latest approaches that they have and how they can be best implemented. So that would be kind of our next step, is more of these types of workshops that are focused around controls and better education around that.
Thank you. 2 more I got queued up for you from Ed. Have there been any studies done here in BC similar to the one you showed for Toronto?
Yes, we have. We were in BC in July, or no, it was June. And we did do some analysis in Kamloops, Prince George, and Burnaby. So we do have some data there, similar to this on 3 different case study homes.
Thank you. And we will be following up after the webinar too with contact information, so people can maybe reach out and
yeah,
if
absolutely.
They want.
Yeah,
great. From Patrick comes, has NRCan completed similar work for hydronic air-to-water heat pump systems? If not, is this planned? These systems have become popular in Europe and can still be combined with existing forced air systems.
So we do, it's in the plans to develop a hydronics workshop. This particular analysis we could replicate it for hydronics. We haven't done any yet. Our primary focus right now was developing more the piece around your limited. So we're looking at retrofits. We were particularly interested in, oil retrofits where we have high temperature radiators that we're retrofitting to heat pumps, and we're typically limited by how much capacity these radiators will have and how much of the heat pump we can run. So we do have some analysis there that could be used to come up with this, but we haven't done it yet.
All right. Last question, I think, and there's been a lot, so thank you so much. From David comes, are there similar analysis and recommendations for commercial buildings?
I'm sure there are. Controls in commercial buildings are a lot more complex, I would say. So it's going to vary from building type, if you're looking at MERBs, or if you're looking at kind of a hospital or a school. It's all going to kind of change with the occupancy. And so I know our team is looking at new MERBs from our side. So we are looking at, what are best practices on mechanicals, and controls would be part of that conversation.
All right. You can take a break. You've done it. Oh, wait, no, one more at the last minute here. From Dan, best control approach for cost alone for natural gas backup. Best control approach for cost alone for propane backup. I'll kind of put that in the, do you see the Q&A button? I think he's asking
Yeah.
kind of two different
So-
scenarios. Yeah.
So for if we looked at propane backup, how would this analysis change, I guess, is kind of what
Best control approach
you're
for cost alone for natural gas backup. I believe that's the,
Yeah, so it'll look a bit similar, I think, because propane is a bit more expensive than natural gas. You'll see, yeah, so where the heat pump is running, the bulk of the cost is already in the heat pumps. That's not going to change a lot. Where you're going to see a change is that on the hourly economic and the single point economic, those points are going to be at colder temperatures. You're going to get more heat pump usage in those two approaches. Actually, the hourly economic approach wouldn't really make sense for most propane users because there's not, well, actually, it would still make sense, but you're essentially you're going to get more heat pump usage in both scenarios, and then end up with kind of a slightly higher cost, likely, is what I would expect. So that gap between that worst performer and best performer is gonna start shrinking with propane.
all right. I think we're going to call it there. We got 1 minute till 1 o'clock, so we timed that out well. I want to thank Jérémie, Mary, thank you so much for joining us, both from HVAC Designers of Canada and from CanMed on Ottawa. A lot of fantastic information here, and we'll get it up online as soon as we can. Any parting words for our audience?
No, just wanted to thank everyone. Yeah. So thanks for the invitation, and Mary for having us, for inviting me to this session, and looking forward for your next webinars.
Yeah, and likewise, you came with some great information. Oh, is that Mary? Can we hear her?
That is, yeah.
Oh, okay. Any parting words, Mary?
I just wanted to say thank you as well for having us, and thank you to Jérémie for such a informative presentations.
Absolutely, and thanks for attending. It's the attendees that make these things impactful and spread the information, and reach out if you got any more questions. But with that, put you back to your day, and we'll see you next time. Thank you so much.
Thanks, Ron.
Cheers.